let's talk about simple circuits, basic. So embodied in these simple equations, V equals IR and P equals VI, the power equation, and Ohm's law, we use this to solve circuit problems. It all seems very simple, but embodied in there is some pretty sophisticated physics, and so we really want to try and push ourselves to understand circuits in some depth. So a simple circuit is a battery, a power source, a battery, a power consumer, a light bulb, and a switch to open and close the circuit. The switch we could even eliminate. But we need a power supply, which is usually a battery or an electric power supply, and some source of consumption of energy. And, you know, this is a battery in a case, and a light bulb and a switch, and here's a familiar flashlight battery and a diagram of a switch and a diagram of a light bulb. This is a photograph of a real situation. This is a diagram. But usually we schematicize that diagram so that it looks like this, with the battery, the switch, and the light bulb. But generally we'll go even further and just call the light bulb a resistor. And represented by that symbol for resistance, and a switch, and the battery symbol is a long line and a short line, and the short line is negative and the long line is the positive. And so we have three things going on here. We have the battery, and we measure its ability to deliver energy by its voltage. So voltage is an energy-related concept, and when we talk about voltage, you'll see in a minute that we always talk about the voltage difference between 2 points. So voltage, a voltmeter always attaches at 2 points, and it measures the electric potential difference between those points. So if this is a 6-volt battery and we put our meter leads at these 2 points, it'll read 6 volts. If we reverse the meter leads, it'll read a negative 6 volts. And that means that the battery is a source of energy at the level of 6 joules per coulomb. That's the voltage. And if the switch is closed and we have a circle, a place where the current can circulate, then the resistance offers resistance to the flow of charge. So that flow of charge we call current. And current we define as the rate at which charge moves. So current in a precise sense would be the derivative of Q with respect to T, like a velocity. But if it's constant, we can just write delta Q, delta T. How many charges per second go past a point? So whereas voltage is measured between 2 points, the energy difference between 2 points, current is a flow quantity, and so it'd be measured like how many charges per second flow through the battery, how many charges per second flow through the resistor, how many charges per second go through the switch. You go to a point, like you're counting traffic, and you count the charges that go past the point. And so that means when an ammeter is put in a circuit, and we'll talk about this later, it has to be in parallel. You have to open the circuit and insert the meter so that the charges go through the meter rather than in parallel. I'll just show you this quickly. Where is is it? I thought I had that. Oh, here it is. I'm skipping ahead a little bit. So you see here our simple circuit, the battery or the cell. Here's our switch. Here's our resistor. If we want to know the voltage across the resistor, and notice I'm saying voltage doesn't go through, current goes through, voltage across. So through and across, remember those are key words, don't mix them up. Current has to go through. If I put the ammeter here, then the current going through the circuit would divide. Part would go through the ammeter, part would go through the resistor, and the ammeter would only measure the current that went through the meter, which would be different because of a parallel arrangement than the resistor. So the ammeter has to be in series because any current that goes through the resistor has to go through the ammeter. And since it's in series, we want the ammeter to have zero resistance. We don't want it to affect the circuit. On the other hand, when we put the voltmeter in parallel to measure the voltage between here and here, we do not want current going through the voltmeter. We just want to read the voltage difference, the pressure difference, so to speak, between these 2 points. And so the voltmeter has a very high or infinite resistance. They're actually opposite in the way that they're built and opposite in the way that they're used. So this is an important fact or feature about meters that you need to know. Unfortunately, we're not in laboratory, so you're not actually going to get to use meter and use them as ammeters and use them as voltmeters and make the proper connections. But it's important that you understand that. Okay, let's go back. So here's our basic circuit, and we measure current and we measure voltage, and how much current we get will depend on the resistance, and that's Ohm's law. So if we know the voltage and we know the current, we can measure the resistance, or if we happen to know the voltage of the battery and the resistance of the resistor, we can determine what the current would be. Or if we knew the current, measuring with an ammeter, and knew the resistance, we could determine what the voltage would be across any circuit element. And you'll see when there's more than one circuit element, it's important where you put the meter. So if I put my ammeter, so one lead was here and one lead was here, I would be measuring the voltage across the battery or the voltage across all 3 resistors. So if I just want to know the voltage across this resistor, I would have to put the 2 leads here with the meter in parallel with R1 or R2. And in a circuit like this, what has to be the same is the current, right? Because there's no junctions, no branches. So as the current flows here, it has no place to go. If 1 amp goes through here, 1 amp has to go through here, and 1 amp has to go through here. And make sure you understand this. 1 amp goes through the battery. The current doesn't leave the battery and go in here and not go through. It goes through. The battery, this is an important concept. The battery is a charge pump. It does not supply charge, it supplies energy. The charges are in the wires. They're like pipes full of water. So a pump doesn't supply water, it just moves water. And that's what a battery does, it moves charge. So remember, a battery is a charge pump, and the voltage difference between the 2 sides is like the pressure difference at 2 ends of a pump. That's another important concept. Okay. Okay, so we have Ohm's law that relates all this and allows us in any given situation to do the calculations we want. And since a battery supplies energy, and the resistor uses the energy, we usually ask about power, because you could say, oh, how much energy does this supply? Well, it depends how long the battery is running, or how much energy does a resistor use? Like, how much energy does a light bulb use? Well, it depends on how long it's on. So to make it independent of time, we use the power concept. And remember, power is energy over time. So it's the change in electric energy over time. But energy is the charge times the voltage, and if you divide it by time, you see charge over time is current. So there's where the P equals VI comes from. And we know from last week that it can also be written as V squared over R, or I squared times R, by substituting Ohm's law. So those are the two things we want to know when we do circuits. We want to know, oh, what is the voltage at every circuit element? And what do I mean every circuit element? Well, we're going to look at circuits that aren't quite this simple for the most part. So if we take this circuit, let's take them both. Parallel, we know all about this, right? From capacitors. Series. And then we have circuits where we combine the two, series and parallel. And that's the assignment, right? So what should be clear about series is, things you want to understand about series is that in this case, the battery is going to supply a current, and there's only one path. So you need to label things like V total or V source, and then I total, and then I1. I1 is the current that goes through resistor 1. I2 is the current that goes through resistor 2. I3 is the current that goes through resistor 3. And because it's series, automatically you can see, you don't have to memorize this, it's physically obvious that there's only one current in this circuit because it's a closed series loop. And the current I1 is equal to I2 is equal to I3 and is equal to the current, remember, a charge pump, the current that goes through the battery. So there's one current here. And to find that current, you know the battery voltage, but you don't know the voltage here, or here, or here. You only know the total voltage. So if this is 12 volts, you have to add these resistances. And it should be obvious that when you add resistors in series, you increase the resistance of the circuit. So in series, you would add R1, R2, and R3. And if this were 5, 6, and 7, that would be 11, 18 ohms. And if this were a 6-volt battery, you would take 6 volts divided by 18, and it means you would have 1/3 of an amp going through each of these resistors. And once we know that 1/3 of an amp going through each resistor, we can then find the voltage. And so when you use this equation, you want to write V1 equals I1 R1. So V1 is going to be I1, the 1/3 of an amp, times the 5 ohms that I mentioned for this, right? Just so you're not getting lost. This is 5, 6, and 7 ohms. Just quickly made those up. And so this is 6. It's 1/3 divided by 5, right? I'm using V equals IR. So the I is 1/3, right? I'm doing V1 equals I1 R1. So 1/3 times 5 ohms gives you 5/3 volts. And here you have 1/3 of 6, so you would have 2 volts. And here you would have 7/3. Seven times 1/3 or 7/3 volts. So if you take the 5/3 and the 7/3, you get 12/3, which is 4, plus 2 is 6. So you can see that in this case, the total voltage, so the voltages you see add. This is sometimes called a voltage divider. The 6 volts here, there'll be 5/3 of a volt here, 2 volts here, and 7/3 here, and that all adds to the 6 volts. And this leads to the idea that we'll talk about later, Kirchhoff's law, which says the sum of the voltages in a closed loop have to be 0. So this would be considered a positive 6. This would be a negative 5/3, a negative 2, and a negative 7/3. And when we added all those, we would get 0. If we go to the parallel circuit and just keep the same resistances, this is 5, this is 6, and this is 7. Now we have our 6-volt battery. But in parallel, the voltage is the same. You see, every resistor is independently connected to the battery. So this is the whole lab problem of unscrewing the light bulb. If I unscrew resistor 3, it doesn't prevent current from going through here. Whereas if I unscrew resistor 3 over here, it's like opening the switch and stops the current. And you'll see this situation when you do the lab, which will soon be posted. Okay, so in this case, what do we know? We know that the voltage across each resistor, if we put the voltmeter here and here, we'll measure the voltage across here. If we put the meter here and here, we're actually measuring the voltage across any of these things because they're all independently connected to the low side of the battery, and this side is all independently connected. So when you're in parallel, and you remember this from your capacitors, the resistors are, the voltages are all the same, but now the current's going to be different, right? Because there's different resistances. So the current from Ohm's law is the voltage divided by the resistance. And so if I'm going to do this, I'm going to write I1 equals, and make sure you use the subscripts, equals V1 over R1, because that's what you got to do. If you don't do it that way, you'll get yourself a mistake. And so what we have is 6 divided by 5. And so what's that? 1.2 amps. And then here we'll have 6 divided by 6, so that's 1 amp. And so you see, by adding, if I take R3 out, the total current will be 1.2 amps. But if I add R3, I'm going to get 7/6, which is what, 1.16 repeating or something like that amps. And so actually by adding a resistor, the battery puts out more current, which is equivalent to lowering the resistance. So resistors in parallel lead to a lower resistance. So if you have a 5, a 6, and a 7, and you add those, like we did with capacitors, 1 over the resistance parallel will be 1 over R1, right, plus 1 over R2, etc., you'll find that you'll get a smaller resistance than the smallest resistor. In other words, what I know is the resistance of 5, 6, and 7 in parallel has to be less than 5. In fact, I can almost guess, because if I had 3 6s, if this were a 6, and a 6, then it would be 1/3, or it would be 2 ohms. So I'm going to guess this is around 2 ohms. I'm going to just pause and calculate that. So anyway, if you add 1/5 plus 1/6 plus 1/7, and then you invert it, you get that the equivalent resistance of a 5, 6, and a 7 in parallel, that the total equivalent resistance is equal to 1.9626, etc. So about pretty close to 2, about 1.96 ohms. Okay, I think I've covered everything I want to, so good luck on the assignment.